Okay, welcome everyone. We are delighted today to invite our departmental seminar speaker, Dr. Anita Parbhakar-Fox. Anita is an ex-RSM alumnus graduating in 2005, was it?
Correct.
Was it in geology?
It was environmental geology, yeah.
Environmental geology. So she knows many of the staff here very well. Currently, Anita is the group leader of the Mine Waste Transformation through Characterization group at the W.H. Bryan Mining and Geology Research Centre, which is part of the Sustainable Minerals Institute at University of Queensland in sunny Brisbane, Australia. Her research is focused on mine waste characterization to improve mine planning and waste management. And she's really looking at developing new tests and protocols for improving waste characterization. And she is passionate about mine waste and her war. She has a war on mine waste, looking at ways in which we can improve problems and find new products for mine waste. So more recently, Anita's led industry and government-funded projects characterising a range of mine waste materials to evaluate their economic potential. And that's what she's going to be talking about today in a seminar. You can ask questions through the seminar in the chat, and we will answer them at the end. Or equally, at the end, you can just raise your hand and ask a question directly to Anita. So with that, I'll hand over, Anita. Thank you very much.
Great. I'm going to share my screen, so if I don't do it right, just yell at me. All good? Excellent. Okay, so good morning from the future. I am in Brisbane right now, so it's my evening, but it's a real pleasure to speak today in the departmental seminar. I think the last time I gave a presentation at Imperial would have been my MSci research project sort of final seminar, and I remember being very nervous, and so it's really nice to be here today to talk to you about what we've been up to up here in Queensland in my research team, but also just share some highlights of the research that we've been doing. And, you know, perhaps if there's time at the end, and I guess one thing I haven't learned since leaving Imperial was time management. So I have got a number of slides here and I hope to get through the majority of them. But if there is some time at the end of today's seminar, it'd be great to sort of have a bit of discussion in terms of what you've been up to in your research projects in this particular space, and I guess seek those linkages. So I guess when I started back at Imperial, one thing that I was really interested in was climate change. So I guess when I was undertaking my A-levels and things like that, I used to spend a lot of time reading the IPCC reports, and I guess I was kind of fascinated in terms of, I guess, the impact that humankind had had on the climate. And I suppose there was that, you know, maybe a lot of students go through that process of kind of just really thinking about the impact that we're having and sort of trying to explore what we could do differently in terms of applying our research and our sort of, I don't know, our sort of higher level training to actually sort of start making a difference in terms of, you know, steering the ship away from the dramatic futures that they were predicting. And I guess one thing that, you know, since leaving Imperial, I probably stopped reading these reports as much as I should have done. But, you know, since leaving, things haven't really turned around. And I suppose back in the day, or particularly at that time, and being a sort of a child growing up in the Thatcher era, you know, we were thinking about climate change, and we were sort of very much aware of kind of the impacts that we were having, etc., etc. And, you know, if we look at sort of what's happened in the time since I left Imperial to now, we can certainly see that we haven't done such a great job in terms of implementing the changes that we thought we would to actually turn things around. And so I guess the reason I'm talking about that is because it kind of links quite heavily with mining, and I'm sure many, of course, all of you are aware of the links between mining and decarbonisation and so forth. But one thing that I really like looking at, and I don't know if you guys look at these too, but in every year, you know, Ernst & Young, they publish their risks in mining, and quite surprisingly in 2022, or maybe not so surprisingly, decarbonisation was ranked as the #2 risk in mining. Certainly many businesses have been thinking about what they can do to sort of reduce their CO2 emissions across, you know, all the different scopes and so forth.
Oh, I think we've lost you there, Anita.
Hello?
Oh, we lost you there for a second.
Okay, sorry about that. Am I back now?
You are back.
Excellent. Sorry. Okay, so I guess I was just talking about sort of and highlighting that decarbonisation is obviously a major risk in mining right now, and it's probably one of these ones that's going to be set to stay in, you know, decades to come, unless something very significant happens to change this pecking order. And as I said, you know, many companies are already sort of thinking about what they can do, and they have been for a little while in terms of reducing their sort of scope emissions across, you know, 1 to 4, etc. And I guess, as I also said, like mining has a massive role to play in this transition towards decarbonisation. I think Richard Harrington and you guys would be across this paper. It's probably one that's mandatory to read in your courses, but certainly Mining Our Green Future was one of the biggest kind of, I guess, papers that came out that really across all sort of media channels kind of connected with people across different sectors, you know, everything, to actually talk about the important role that mining has in that transition towards the green energy revolution and decarbonisation. So, you know, I guess even here in Australia, this paper was really well received. And so that's something to note in terms of, you know, building some momentum for change. And as I did mention, I hope it wasn't when I cut out, mine waste has a big role to play in this transition too, and we will get to that. So I guess, you know, it's great that we want to push towards the low carbon economy. And as you know, the person going to Imperial back in 2001 was very worried about climate change. So, you know, now that we're actually making some real progress, it sort of feels like we're suddenly making that real progress towards decarbonisation, which is great. I mean, if we look at sort of these graphics from the Visual Capitalist, you know, they very much speak in sort of quite very powerful terms of the amount of copper that we will require if, you know, we're going to go towards, you know, fully EV. You know, in some countries, now India reckoned that by 2030 they'd be fully EV, which is doubtful, but certainly I'm sure they'll make a big push towards increasing their EV footprint or uptake. However, the flip side of this is more production of copper obviously results in more production of mine waste. And so if we look at sort of the amount of, you know, if we look at the global tailings that are produced right now by commodity, copper far outshines all of the other sort of major commodities in terms of the contribution to the global tailings volume that it produces. So 46% of all tailings produced come from the mining of copper. So if we're going to require all of this additional copper, and some say 9 times more by 2050, we're going to produce a significant additional volume of mine tailings. So in terms of, you know, mine waste management and thinking about what we're going to do with all of this mine waste materials, problem's only going to get worse. And we know the major problems associated with tailings are geotechnical and, you know, geoenvironmental, and I'll show you a couple of examples of that. But, you know, the problem is appreciably only going to get worse when it comes to managing that waste. And, you know, I was talking to somebody from a major mining company actually based in South Africa a couple of months ago, and she made this great statement, and it's really sort of stayed with me. And I say this every time because if we think about like the Paris Agreement in, I guess, 2015, you know, that was only sort of 5-6 years ago, but she made this statement that mine waste is where CO2 emissions were 5 years ago. So right now we are at this critical point where we can actually start to do something different with our mine waste. So in 5 years' time, 6 years' time, we're not having these kind of conversations at like COP, whatever number it will be then, around kind of the management of mine waste. So we've, you know, I just think that right now is just a really critical moment to actually start implementing some big changes in terms of what we do with our mining waste. Now, going back to the Ernest Young risks in mining, now coming in at number 1 was environment and social. And to many of you, that may not be a massive surprise. I mean, when you think about some of the things that have been said in the media in terms of social engagement around, let's just sort of mention Rio Tinto and the Juukan Gorge. I mean, that was not a great moment for the mining community. But, you know, other things have been going on too. So, I mean, acid and metalliferous drainage, you know, it was stated that after climate change, I think the UN had actually said that AMD formation or AMD impacts was actually the number 1 environmental risk, or the number 2 environmental risk after climate change that was actually being posed to our global community. So, you know, things like that are really significant, and they, you know, they kind of feed into why environment and social are positioned at number 1. So there's many different risks associated with mine wastes. And, you know, again, just to highlight kind of the scale of the problem, you know, we talked a bit about copper tailings, but, you know, everyone knows what happened at Brumadinho, and I will get to that. But certainly what a good thing to come out of Brumadinho was obviously everyone then sort of evaluating the tailings storage facilities that they had to kind of evaluate whether or not there were stability risks. So focusing just on geotechnical stability, one of the teams up here at UQ kind of pulled together a lot of data. And I guess this kind of summarizes kind of some of the numbers that sit behind the amount of additional tailings that we think we're going to need to produce in the coming years to meet kind of current demand, and not even sort of that future demand that we predict. So, you know, 13 billion tonnes of additional tailings per year will require storage in existing or planned facilities over the coming 5-year period. That's pretty staggering. I mean, it's pretty hard to conceive like how much material that is. And so again, deferring to the visual capitalist, you know, they put out this wonderful graphic here, which kind of just shows, you know, the amount and the scale of materials that we're dealing with, and we will need to improve the management of as we move towards that low carbon future, given that we're going to be producing more. So that's obviously Manhattan and New York that you can see there for scale. It's not just mine tailings, though, and I think as we've kind of seen the disasters around mine tailings, there's been a big focus on, you know, improving tailings storage facilities, which is fantastic. But don't forget about the waste rock, and don't forget about the metallurgical slags. There's many different types of mine waste materials, and you know, this is a graph by Gavin Mudd, who's down here at RMIT. You know, he's a big data nerd, and it's probably a little bit out of date, as we can see here from 2015. But the general trend is showing that across all sort of industries, as we mine lower grade, larger footprint deposits, we're obviously producing more waste rock material across all sectors. And you know, one might argue that we don't actually mine all, we mine waste, which I think is arguable. But in terms of the total volume of all of the different mine wastes that are produced, then this statistic came out a couple of years ago, from a researcher at the University of Queensland, who summarised that 100 billion tonnes are produced per year across, I guess, the mining sector in terms of the total amount of waste produced. And, you know, there isn't a visual capitalist graph for that, but what there is a photograph like this. So this is from the National Geographic, which I've very kindly borrowed. Thank you, National Geographic. But what you can see here is this is Bingham Canyon. And I'm sure many of you have been on field trips or would have liked to have gone on field trips, what with COVID and everything. But you can kind of see, you know, the pits here at Bingham Canyon. But probably when you go on these trips, the things that you don't spend too much time looking at are the mine waste deposits or the mine waste dumps all around, I guess, the peripheral of the open cuts and so forth. But you can see, you know, in terms of like, you can see these deep gullies forming here from all of the runoff. So you can tell this is a very dynamic environment. You can see that there's active oxidation processes going on here with the color changes and so forth. And, you know, so far, $400 million US has been spent on cleanup efforts around the mine. And that's really just scratching the surface in terms of, you know, they're dealing with masses of arsenic pollution, AMD, etc. There's many challenges that are going to be faced to restore this particular environment. So that's kind of one of the challenges. Like, how do you restore an environment like that? What do you actually do with this material that means that you can actually break that source pathway receptor chain, that pollutant linkage chain? So, you know, if we go back to Brumadinho, I mentioned this before. I mean, for someone who works in mine waste, I've been working in mine waste, I guess, since I arrived in Australia in 2006. Yeah, 2006. But what we can see here is Brumadinho, and you must remember when this happened, early January 2019. So the tailings storage facility broke, essentially, causing a massive rush of tailings across the mine site. It resulted in, you know, a huge volume of tailings being released. Over 240 people lost their lives. 100 are still missing, obviously presumed now dead. And that was a really significant loss of life. I mean, I know that natural disasters occur and far more people unfortunately lose their lives in those. But, you know, this, for many people, it was utterly preventable. You know, the monitoring systems have been in place, and, you know, there's been a whole sort of report by sort of international experts sort of unpacking what actually happened and sort of attributing where sort of faults lie, etc. And we're not going to talk about that. But I think what was most shocking about this was 2019, but in 2014 and 2015, you know, there'd been the big failure at Mount Poli, and there'd also been another big failure in Brazil too. So, you know, systematically, it sort of highlighted to the global community there's a problem with geotechnical stability of tailings storage facilities, and something needs to be done. And something was done. So I'm not going to labour the point here, but, you know, the thing that did come out of this awful disaster, which was, I guess, the straw that broke the camel's back in many ways, was that the global tailings standard was developed, and that was developed and published last year. And all the mining companies now are sort of evaluating their tailings storage facilities, looking at sort of the standards. I think there's 17 points within the standard. And they're evaluating how they need to amend what they're doing to actually be compliant with the new standard, which is really great to see. And certainly future tailings storage facilities will need to comply to those new standards. And, I guess this was just showing what the impact that these failures that I just mentioned had on share prices. And so, for the financiers, and, I guess one of the big drivers for putting the standard out, it was around, the financiers sort of saying, we need to do something better. And it wasn't just about the loss of life. I guess it was thinking about the financials too. And certainly, these big impacts, or these big disaster events certainly do impact in that regard too. So maybe that was a driver for that standard, but certainly the outcome is a positive one. I guess here I wanted to touch on what I'd said earlier about, acid mine drainage being one of the biggest risks. I had a little video here which is a real shame, because what it was playing was some footage that I took down in Tasmania, but basically it was showing you acid mine drainage sort of being deposited into a clean river system. So there's a Mount Lyell mine site in Western Tasmania, and it's probably one of the worst examples of acid and metalliferous drainage in Australia right now. So, from one of the underground adits there, AMD's coming out, it's, hitting the Queen River, which essentially was a clean river up until that intersection. And at that confluence, bam, the pH decreases to in the order of, 3, sometimes maybe a bit less, but for that entire riverine system, it's completely devastated. And so I would have shown you examples of that compared to sort of Tarcombe wilderness. Can't show you that because my video doesn't work, but certainly I guess it just highlights the point that it's not just the geotechnical risks that we have to think of as we're talking right now. This active process is going on right now, and it's 2021. Like, there should be a solution to actually help the state government of Tasmania remediate and prevent that from happening. I mean, what you can see in this water, well, you can't, but what we've measured in the water is that, there's very high levels of copper in this water, which, I guess that the hydrometers online today will tell you is very easy to recover in this form, and it actually is. So why aren't we doing it? So I guess, part of the challenges that we face as we move forward around mine waste is actually sort of changing the narrative around just leaving things like this to occur, and actually, given that we've got the technology, applying it so we can actually clean and remediate. But certainly, maybe the driver, isn't going to be restoring the environment back to the Tarcombe wilderness. Maybe the driver will be to actually recover the copper and actually have saleable copper to meet that future demand that we need to actually transition to the low carbon future. So I guess something to think about there. And I guess this was just to highlight, if we don't change. If we don't turn things around in terms of climate change, it's going to have a big impact on mine waste. And so I guess what this diagram is sort of summarising is the sorts of impacts that will occur if climate change is not turned around. So you can see here in terms of waste rock piles, we'll have increased amounts of acid and metalliferous drainage forming, increased rates of oxidation of the sulfides, more pressure will be put on tailings ponds, more likely to see structural weakening. So there's a lot of reasons why we need to do something for climate change, just fundamentally to sort of negate some of the really bad impacts that we have on mine waste if we continue to produce the same amount of material that we do right now, if not more. So there's also something in it for us. So I think we need to take a systems thinking approach when it comes to sort of thinking about these global challenges and mine waste. So I guess that's kind of a bit of a background, setting things up. What I want to talk to you now is about Australia. So I guess I got on a plane in 2006 and I went down to Tasmania, and I've had a great opportunity to get out and about. So what you are looking at here, and for some of you this may surprise you, but this was data collated from the state geological surveys. And so the state geological surveys, they keep records of all of the active and inactive mines. And we're talking here quarries, metalliferous mines and coal mines and sort of all sorts of scales. And, obviously you guys know that Australia is the land of mining, and this very much conveys that. So what I want to show you now is some stats regarding each of the state or how the states perform in a range of ways. So if we look at the number of active sites across, all the different states in Australia, certainly we can see that Victoria and New South Wales, lots of active mining. But if we start to drill into some of the other things that perhaps aren't so pretty to start thinking about, terminated and seized mines, we can see that in New South Wales there's just under 20,000 terminated mines. Okay, fine. We can appreciate that mines have, a natural life cycle. That's completely fine. Not too worrying there. But certainly in terms of scale, you can see that there's a bit of a difference in terms of sense of scale. Victoria and WA, it's not that they don't have any, it's perhaps that their state geological survey didn't capture it when Werner was going through the data. So some of these graphs may be a little misleading because they may imply that there's nothing, but it's actually more that there aren't entries in those state geological databases that were evaluated for this for Werner's research paper. But I think the thing that becomes a bit more shocking to me is when we start looking at the number of neglected mines, certainly there's quite a lot of those across, the major sort of mining states here. Queensland, I suppose, in this regard is not doing too badly, considering that in Tasmania there's over 1,000 more, and we consider the difference in terms of the mining sectors in both those states. That's quite interesting. But this is the one that really gets me. So, again, it's a bit skewed. Don't think that there's none in Victoria, New South Wales, Queensland, Tasmania, or the Northern Territories. It's just that they're not listed as signed off in those geological state surveys. But we can see in WA, compared to sort of some of the other numbers here, there are sort of just over 3,000 rehabilitated sites registered there, but there's none in the others. And to me, okay, I know that I did say don't sort of think it's zero, but there's no, I couldn't tell you an example in Tasmania where it's been signed off, and I'd lived there for what, 13 years. In Queensland, again, it's really, there's probably the Ackland mine now, which is probably one of the closest examples, but there's not that, it doesn't roll off the tongue in terms of the number of rehabilitated sites. So whatever it is that we're doing right now, when we close a mine and think about managing that mine waste in perpetuity, it's obviously not working. And so if we go back to looking at those active and inactive mine sites in Australia, but if you haven't been to Australia, I wanted to share this because this just shows you the diversity of the challenge that we're facing. So these are sort of some of my happy snaps from some fieldwork adventures that we'd had over time. But you can see that diversity of mine waste. I mean, this is mine tailings in northern Queensland. This is mine tailings in northeast Queensland. This is northwest. This is down in Savage River. This is which is in Tasmania. This is on the other coast of Tasmania. You can just see that all of these different environments are so different. So actually just thinking about, just taking a standard approach to how you go about sort of just remediating, it's not necessarily going to work because the mineralogy is obviously appreciably different. Like, we're all geologists sitting here in this sort of virtual room today, and we know that all deposits are complicated. There's structural alteration, there's structural mineralization sort of related events, structural deformation, there's alteration events, there's supergene, there's all sorts of things that are going on that are going to alter that mineralogy. So in terms of actually understanding how you're going to start, characterize or rehabilitating these sites, it fundamentally requires you to have characterized these materials thoroughly. So I think sometimes when we work with some industry sponsors and so forth, they go back to mine sites and they think they can just simply reprocess them because they've read some reports and looked at some assay data, and it's fundamentally not correct. Need to look at the mineralogy, need to actually have a good look and a good understanding, because once you've got a good handle on that, then you can start thinking sensibly about valorization options. And so, look, I'm not going to go into this, but, I've bagged out a little bit mine rehabilitation practices. Certainly there are some good resources out there. There's the GARD guide, which is the global ARD guide, which is kind of a wiki style thing. But, in terms of looking at the advice for mine closure, this is kind of one of the diagrams that I like to pull out. So, if you're going through different parts of your life of mine, these are the sorts of things you could start thinking about in terms of your mine rehabilitation, mine closure. And, in Australia, we have guidelines too, that, a nice little tiny book that's going to tell you how to develop your mine rehab plans, etc. I don't know that they're working. I mean, if we think about some of those examples that I showed you and the video that I may have played to you, to me, it feels like this: Band-Aids don't fix bullet holes. And, very much here is a really nice example of that. So this was an abandoned copper and tin mine in northeast Queensland, and it fell to the government to manage this because I guess the site owners defaulted. And, in a quick fix effort to try and retard the formation of acid and metalliferous drainage, they put a plastic cover over the top. And, a plastic cover like this is not going to do anything in the Queensland climate, which they very rapidly found. And since then they have gone back and they've sort of put a proper clay cap over this particular waste rock dump, which is actively generating AMD. This is like the most beautiful rocks I've ever seen. They are like massive sulfide boulders just sitting there. But at this point, even putting the clay cap on, you know, the AMD engine has kicked off. So in order to actually switch it off, we're going to actually need to have to do something a bit more serious. So I'm not convinced that the traditional mine rehab methods are actually working. So we need to do something different. And I guess this is where I mentioned the pollutant linkage chain earlier, but we need to actually just start thinking about this from the source. We need to characterise the materials, identify re-commercialisation opportunities. And I think one thing that I've sadly learned in my time here is that as much as I used to go out beating the drum and sort of saying to people, oh, you know, you should do AMD prediction better because you should care about the environment and you should care about reducing your long-term environmental liabilities. And people would give me 5 minutes, they'd listen to what I was saying. Some people would even sort of, you know, take the proposal and, you know, put a little bit of funding towards it. But now when you say to companies or governments or whoever's sort of prepared to listen, that, you know, let's actually go back and have a look to see if we can actually pull out some of those critical metals and copper that we need to actually transition to that low carbon future. The conversation's rapidly changing now. And so I'm all for economic rehabilitation in that regard. So critical metals have been a big driver for this economic rehabilitation idea. And so what you're looking at there is Australia's critical minerals prospectus. I guess the 2022 one should be issued early in the new year. But certainly in terms of, you know, every country, every continent has a slightly different interpretation of what critical minerals are actually on their list. And I guess this kind of highlights the ones that are probably on our Australian list. And so there's the usual suspects, lithium and cobalt, and certainly lithium's been going off its chops in WA in terms of, you know, becoming a very globally established lithium industry, which is great. But certainly here in Queensland, we have an opportunity to look at, you know, some of our copper deposits and see if cobalt actually is, you know, a byproduct of some of that copper mining activity. So maybe those mine waste dumps are actually significant repositories of this critical metal that we're so desperately seeking to actually facilitate that transition. And I guess going back to the visual capitalist, who I really should just work on commission for. But, you know, again, this beautifully summarises the different metals that are required for some of these clean energy technologies. And you've probably seen this 1,000 times, so just, you know, humour me and let me just go through it. But certainly, you know, we can see cobalt, critical metal that's endowed in Queensland, indium, I'll talk a little bit about that. Copper, we've still got quite a lot of that in some of our dump sites, which I'll talk about. And nickel too. If we look at the signatures of cobalt in our mine waste, what we're commonly seeing, and it's obviously no surprise to you guys as geologists, but, you know, cobalt and nickel sort of are co-locating in the waste that we've been evaluating. So there's an opportunity there to recover that too. So I guess our research has very much been focused probably in the cobalt space to date. We've certainly had a bit of a crack at looking at indium and rare earth elements, which we will continue to in the next little while in our project. So I guess, how does this apply to what we've been doing in Australia? So I'm just going to quickly walk through some examples of the type of work that we've been doing. So here you're looking at a map of Tasmania. So if any of you aren't familiar with Tasmania, it is a part of Australia. You know, despite there being this divide with the Bass Strait, you know, I think sometimes mainlanders forget about Tasmanians as being part of Australia, but they certainly are. It's not part of New Zealand. It's a fantastic place to go if you love ore deposits, if you love, you know, hilly landscapes, if you love acid and metalliferous drainage and mine waste landscapes. It's a perfect place to go and visit. But certainly what you're looking at here is a map of net acid producing potential, and this was drawn in the late 90s, but it was published in 2001. And so, you know, the Office of the Supervising Scientist went down to Tasmania, mapped out sort of the hot spots of where, I guess, hot rocks in terms of AMD formation were located. And no surprise, they sort of the hot spots correlate to our major mining activities in the west coast, and a couple of sniffs also towards the east, and they probably correlate with some of the tin mining activities. But I love to share this map because to me it means something completely different. This is a secondary prospectivity map right there, because commonly associated with these sulfides are some of these metals that we've been looking for. Some of these obviously feature on that critical metals list and are necessary for that transition, and some of them, you know, gold, arguably it's on our new economy minerals list in Queensland, so it's on our state list, but, you know, it's not necessarily considered a critical metal, but it is actually present in some of these, so it could sort of be a driver for rehabilitation if you could remine it. There have been mining companies that have been looking at the waste here a bit more seriously. So NQ Minerals, they actually have the Helia mine, which is probably sort of here-ish. And they're actually reprocessing tailings there. So I was going to show you a video about it, but I don't have time today. But certainly if you're interested, jump on and have a look at the Helia tailings reprocessing. And there they're recovering zinc, lead, gold and silver from obviously various sulfides. And, you know, there are sort of other people sort of prospecting and establishing projects too, as I said. Can't talk about all of them right now, unfortunately, but I'm going to talk about one, which is the Savage River. So if you don't know where Savage River is, it's on the west coast of Tasmania here, and that's actually shown the location of the Helia mine there. It's a magnetite mine. It's been in operations for, I guess since the mid 1900s. 3 open pits, extensive mined since 1960s, correct? You know, it's a simple operation. It's not simple by any means. I mean, actually mining in these conditions in Western Tasmania, you'd take a grey London day anytime. This is a really cold, difficult place. And these rocks are the most structurally complicated rocks I've ever seen. And actually, when we do waste rock projects there, and we look at the different waste types they have, you know, in these wet conditions, everything looks the same. It's really like my hat goes off to these guys mining in this particular geographical region. But anyway, you know, metallurgically speaking, though, it's magnetite they're mining. So magnetic separation, that goes to Port Latter where it's pelletized and final products made and shipped off to international markets. But the thing that I'm interested in is the tailings. So associated with the magnetite is, you know, there's a few different ore lenses or bodies, but associated with magnetite is pyrite. And obviously pyrite forms acid and metalliferous drainage. Pyrite's a sulfide, an iron sulfide, it oxidizes, it generates acid, and then we have a problem. And so if we look at some of the tailings deposits that we have sort of at the mine site here, one of them is called the old Tailings Dam, and due to the kind of the ownership agreement of this mine site, it's currently under the management of the Tasmanian state government. And so they funded my very first MSci equivalent student's study in 2014. And what she was looking at was trying to find a way to put all of this material under a water cover. So if you have sulfidic material and you put a water cover over the top, then you can retard that oxidation from occurring, which obviously in theory sounds great. In practice, you know, her project was sort of establishing the minimum depth for a water cover to extend over this area, because we have 38 million tonnes of pyritic tailings impacting the Savage River itself quite significantly. But we established what that depth should be, we published that, etc. But the problem was that if we'd have actually put that water on cover down, we would have potentially caused maybe an impact to the dam wall that you can see just to the south here. So actually, whilst we established the depth, it probably wasn't a practical solution to manage this site. So I guess we kind of had to start thinking about other options. And this is probably what kickstarted my interest in reprocessing. So what we did was we'd taken some sulfide materials and we'd undertaken laser ablation analysis on them. And we found that there was significant cobalt in these materials. And so we did sort of a number of studies, and we did sort of eventually come to a bioleaching study where we kind of tried to work out a methodology by which we could actually recover that cobalt from the pyritic tailings. And so we did sort of bioleaching test work and sort of etc. It's all published here, so I'm not going to go through it. But certainly this sort of approach we developed was mentioned in a landscape review of technologies to reduce or eliminate tailings. So I think it was in some regards, it was a methodology well developed. But certainly I guess the plan was to put back to the site and to the Tasmanian government, you know, potentially this is what you could do to turn around this site. And so really, fortunately, we actually did appeal to the better side of the Tasmanian government, who are very, very cautious with any sort of funding that they have, because they don't have big budgets like, you know, the state governments of Queensland and New South Wales. So they're always very cautious of what they fund. But they did give us some money to go back and basically, you know, tighten up what we were doing. So I guess in this very first campaign here and sort of the work that we've done here, the samples that we got were sort of very much in the upper sort of 5 meters to even less in terms of, you know, representation of the tailings. So we then had the opportunity just now in our Tasmanian winter. So this was my honours student, Laura Jackson, who did the work in 2014, and she came back now. I've managed to convince her to be my postdoc, which is great. So I sent her back to site in a coming full circle kind of way, where she actually was doing sonic drilling into the tailings. So then we could actually start looking at the characteristics of the tailings at depth, because actually the maximum depth of these tailings is in the order of 60 meters. And, you know, that's sort of kick-off study that we did, sort of focusing on the upper 2 meters, great, but we actually need to look at the variability throughout the whole profile. And so I guess our quest for sort of evaluating the cobalt in the tailings there and actually metallurgically recovering it and developing a methodology for that continues. So watch this space. And that's something that we've been doing at some other tailings storage facilities in Tasmania too. So this is the Bobadil Tailings Storage Facility at Rosebery, where another one of my honours students had a bit of a look. And what she found was that there was actually gold inclusions, even in the sort of the shallow materials that she was sampling. So again, upper 2 meters. And, you know, the package of materials there is again, sort of more in the Savage River sort of magnitude in terms of tens of meters, if not sort of higher magnitudes. Certainly we can see there's visible gold there, but, you know, having a good look at the laser ablation results, we can see that there's potentially significant gold, even just in those sort of shallower materials. And when we think about, you know, the complexity of mine tailings management at that particular site, now in the future, they need a new dam or else they're going to have to stop mining. So maybe if going back here and remining this material, extracting gold and finding use for the, I guess, the non-silicate, sorry, the non-sulfide inert gangue materials, there could be an opportunity to win back some space to then redeposit those new tailings. And again, another Tasmanian example, this is Johanna van Balen, another honours student, this was Lexi King. You know, New Century Mine have just recently taken up the optioning on the Mount Lyell mine site, sorry. And basically they've got 2 years to sort of build a business case in terms of whether or not they're going to buy that mine site in Western Tassie. So we did a study on the Princes Creek Tailings Storage Facility, very much looking at cobalt and pyrite again. And so some back of the envelope calculations that we've put together sort of indicate that potentially, based on some sort of back of the envelope calculations, there could be significant value to be recovered from these mine tailings. You know, just considering the cobalt story alone in pyrite. So that's something for New Century Resources to consider over the next 2 years. Now in Queensland, we've been doing sort of similar work, and I guess this is probably a bit of one of those secondary prospectivity kind of type maps when we look at sort of the number of abandoned mine sites across the various sort of geological districts that we have here. But we do have examples of active projects where people are actually remining tailings, which is fantastic. So Century Mine, I guess they first had a crack at, well, New Century Resources first had a crack at the Century Mine, where they're recovering zinc from tailings, which is what you're looking at there, hydraulic mining. Mount Carbine, they're recovering tungsten, which is considered a critical metal. And there's new projects here too, also looking at gold recovery from mine tailings. So there's a couple of new projects that are in development. And Mount Morgan's quite significant because that's one of our, I guess, Queensland's examples of an AMD impacted site. But my team, what we've been doing is certainly we've been looking for more of these potential project sites. So we've been given, I guess, significant funding from the Queensland government to basically go out and just do more of those characterisation studies to work out, you know, where's the fertility and, you know, in terms of ore deposits, what does it relate to? You know, is it related to, you know, copper mineralization? Are we seeing a signature of cobalt in, you know, various different types? And so that's what we've been exploring, myself and my team. And where things actually seem like they are particularly well endowed, then, you know, we can then sort of start to use sort of augers or mechanical augers or petrol augers, I should say, and sonic drills and all other sorts of tools, so we can actually sample the full profile of the tailings. And, you know, the main thing, or one of the highlights of sort of working up at the SMI, is the ability to sort of collaborate with the JKMRC and start pulling out sort of new mineral processing methodologies that are suitable to these kind of partially oxidized materials. And so this is just a snapshot of where we've been, and I know that we're getting close to time. But yeah, certainly in terms of that does play. So you're looking at some drone footage there of one of the tailings storage facilities that we've studied, which is the Capricorn copper deposit here. And we've just recently completed a new geophysical survey on this tailings storage facility to really help us understand the subsurface architecture of what's going on there. So, you know, these are the sites that we've targeted so far, and in our programme, I think we've got another 21 sites to go by 2024 from our Queensland government funding. So just, I guess, in terms of the, you know, I talked about the diversity of mine waste that you can sample, and that's just to give you an example of the types of material that we have sampled in purple. And in grey here, these are the things that we're going to be sampling in the coming year and, you know, further into this particular project. And in terms of what we've been doing, this is just, you probably don't need these details, but, you know, these kind of stream one, these kind of, you know, testing fertility of critical metals programs, you know, they're integrated geochem and mineralogy and laser ablation kind of studies, because I sort of fundamentally believe that, you know, if you do these things and integrate the data, you can actually understand where the value sits and then start thinking about what the metallurgical recovery processes may look like in our Stream 3 program. So I guess we've gained momentum after sort of starting the Queensland Government project in 2020. And we've now got a sort of a significantly funded project from Geoscience Australia, who want to see this type of work occur across Australia. So I showed you all those different mine sites, active and inactive. You know, there's a smorgasbord of sites to be undertaking characterisation work in, and a lot of the state government agencies and Geoscience Australia themselves have realised the value in actually undertaking that and developing some sort of national catalogue of this information. I'm not going to talk about that. I'm going to skip a few slides. I mean, basically, in Queensland, you know, obviously, we'd be foolish to think that there's not a link back to the primary ore deposit. And so I guess if we look back in the literature, you know, we can see, you know, iron oxides, which we have in abundance in Queensland. There's that signature of having high cobalt in the waste. And certainly we have some other types of deposits too, where there's that potential for having cobalt in the waste as a signature too. So I'm just going to show some quick results, and I'm really conscious that we don't have much time left. So what you're looking at there is, this is our whole rock or our assay data of some of the sites that we've been to. And we can certainly see that there's a concentration of cobalt, certainly in this particular area, which we assumed there would be. I suppose our hypothesis was, yes, we'll see endowment of cobalt in the IOCG wastes and certainly in the sediment hosted systems that we have here. And that certainly is. And in terms of, I guess, average cobalt, you might be thinking, wow, that's not too, that's pretty low. But actually, for a workable cobalt project, that's actually like certainly towards anything above 300 ppm, I've been told by various business people, is actually something worth considering. So we can certainly see two of our sites, Osborne and Rocklands, we actually have quite good endowment in cobalt. So that's kind of good. So, you know, I talked about this being an integrated program. You know, it's not just about looking at the assays, which commonly I see is a mistake that some secondary explorers make. No, you have to look at where that cobalt's sited. And so we've sort of done our MLA and our XRD studies to kind of look at the deportment of cobalt mineralogically. And I guess here, this is kind of showing the upgrading. If we just looked at sort of cobalt in the laser ablation data from the mineral, the host mineral that I've listed here, we can certainly see there's a bit of an upgrade in terms of average cobalt concentration. So now, obviously, Rocklands jumps up to sort of, you know, 9,000 or nearly 1% average cobalt, which is pretty good. Again, this is, you know, you probably saw me only speak quickly about that slide, but, you know, we only take up to 80 samples in these campaigns. So this is enough for us to think that there's value in going back and doing a detailed Stream 2 investigation, which is exactly what we did. So we actually got investors from Japan to sort of co-fund a more detailed Stream 2 investigation of that particular site. So I guess I haven't really got time to sort of drill into that, but that's kind of a comparison of the whole rock average cobalt versus the laser ablation average cobalt. And, you know, if you just look at sort of the laser ablation data, you can see concentrating, producing that sort of con of minerals that you need, and then looking at the recoverable cobalt, then certainly there's that opportunity to really upgrade the project and actually, you know, add value. And that's kind of what we're about. So I guess Osborne and Selwyn, you would have noted, was sort of where our sort of gold star was in terms of maximum cobalt concentration. And that's just highlighting what these tailing storage facilities look like. In terms of some of the laser ablation work that we did, I guess it would be foolish to assume it's only one sulfide that's the main host. So what we did here was we looked at, you know, pyrite, pyrrhotite and magnetite and measured cobalt in there using laser ablation again. And so what you can see is that there is sort of reasonable cobalt across all three phases. So I guess if you were thinking about metallurgical recovery and you wanted to optimize your value, then you might need to sort of consider maybe, you know, magnetic separation. Maybe you want to recover this magnetite for a couple of different reasons if you think that the cobalt tenor is worthy. So just things to think about. And again, because this was one of our tastier sites, it was certainly nominated for a Stream 2 investigation. So we just had some bulk materials drilled at site to basically send back to us to start undertaking that metallurgical test work with our JKMRC colleagues. Now, I really don't have time to talk about some of the other investigations, but this is just showing I guess, our first investigation at Rocklands here. So this was back in 2000. Since then, we've gone back, we've done some infill holes, and this was a hand auger campaign. This was a shallow tailings storage facility, so they wouldn't allow us to sort of take a sonic drill out here. So we had to take basically a hand auger and get cracking in terms of recovering those samples from here. So we've got a nice grid that we've now sampled across this. And that's what I'm showing you here. And this is my my poor colleague Torben, who I had to send out on this campaign because I was elsewhere detained doing a similar job. But yeah, this is certainly one where the Japanese Oil, Gas and Metals National Corporation have sort of co-funded this investigation to really see if we can pull out how we can metallurgically recover that. And whilst this may not be the biggest tailings storage facility, I suppose what's in it for JogMeg is like thinking about if we can develop a metallurgical recovery method for this, for these mine tailings, then applying it to other tailings storage facilities of the same sort of geological background means that there's going to be that opportunity to recover that value at other sites too. And maybe this is all moving towards developing a hub for cobalt processing, which perhaps is something that's on the cards for the Queensland state government. Now, I mentioned a little bit about cobalt and nickel sort of co-locating, and haven't got time to talk about this data, but you can certainly see there are some trends. And there's obviously two clusters here, which I probably should have broken out by mineral type, but you can distinctively see there's two different mineral phases here where we've measured that. But certainly in general, you can see there's that opportunity also to think about the nickel recovery too in these mine tailings. A little bit of a weaker relationship when we plot it against copper, that's true. Certainly at this tiny little site we measured here, or we studied here to Pindora, there's quite a strong relationship. So I guess don't presume one and the other are going to couple. Like certainly, doing the laser ablation work, etc., having a good look at the mineralogy is certainly really important to maximise the opportunity for identifying that value. And so, where to next? I guess in the search for copper, for cobalt, sorry. There's a lot of mine sites. Obviously, there's many copper mining activities in Queensland, but certainly we've picked out some here which are operating in abandoned mine sites, which we think fit our sort of secondary prospectivity profile of sites that we're going to go back to target for characterisation in Stream 1. And maybe this is all leading towards the northwest Queensland belt actually being a potential global leader in recovering cobalt from waste and contributing those metals, supplementing our need for cobalt as we move towards that sort of clean energy transition. Obviously, copper has a big role to play in everything too, and so you may have been curious about what our copper in waste values look like, and that's kind of what I'm showing you here. Certainly, hotspots at Mount Oxide and Pindora. So I guess what they look like here, if you were curious, are these two sites here. So this is Pindora. It was an oxide, well, both obviously as the words may suggest, oxide operations here, so not sulfides. But you can certainly see this is a remnant spent heap leach pile here, but you can see this is a small waste rock dump, and you can see the copper mineralisation here, the chrysocolla and so forth. So this is, understandably, there's quite high copper still left on this particular site, and certainly down at Mount Oxide too, and that's very much hosted in a range of oxides, and so forth. So here's just some examples of those sort of types of materials that we've pulled out down at Mount Oxide, and you can see the diversity of oxide materials that we have there. And, in terms of like hotspots across the site where we sampled, that's what we're kind of showing here. So there are sort of particular areas in the footprint where it's a bit more endowed, but certainly this is probably enough information right now for us to use, because we've got bulk samples now of these materials to sort of start that metallurgical investigation of how we're going to recover the value. And certainly the same thing again here at Pindora, that sort of small, really small mine site where there was sort of that heap leach operations. There's less than 1 million tonnes of mine waste at this particular site. Anyway, I'm not going to talk too much more about that right now. Rare earth elements are something that's also being discussed here in Australia quite fiercely, and obviously rare earth elements play an important role also in that transition towards that low carbon future. So in our research, we've certainly pulled out a north-south corridor of hotspots here. The Mary Kathleen mine has quite high rare earth elements in its waste. So formerly it was a uranium mine. You're not allowed to mine for uranium anymore in the state of Queensland, but certainly the signature of rare earths in those mine tailings is quite significant. Just what that looks like across the sites that we've sampled. As I said, at Mary Kathleen, the mean total rare earth elements is 23,000 plus ppm, so that's pretty tasty. And in terms of where that value is hosted, we can see it's hosted in a diverse range of mineralogical hosts across these different sites. And at Mary Kathleen, I'm not going to talk to you about this case study in any detail, but just to show you where the tailings storage facility is, we can see that there were 2 phases of mining, which you can just sort of see in summary there. And certainly that's reflected in the signature of rare earth elements down profile in some of the holes that we've had access to evaluating. So this is based on historic data, because there's a clay cap on the site. We're not allowed to go back and re-drill, so we've had to use some samples that were collected back in 2014 by a consultancy. But you can see that change in concentration, and that's sort of due to those 2 phases of operations. In terms of which rare earth elements are at Mary Kathleen, lanthanum and cerium are very much the things that dominate, and there is a grade by size relationship whereby they concentrate in the fines, which is all information we need when we want to go back and start thinking about reprocessing. So I guess some of the work that we have done in that reprocessing space is looking at sulfuric acid leaches. So our colleagues James Vaughan in chemical engineering, the team have been looking at sort of low temperature sulfuric acid leaches to sort of try and recover some of that value. So that's, I guess, a separate complementary project that's ongoing here. But certainly we always presumed when we went into this project that the main hosts of the rare earths were allanite and stilwellite. But actually, when we sort of did some misfires on the laser ablation instrument and accidentally sort of zapped some minerals that weren't allanite and stilwellite, we actually found some significant signatures of the rare earth elements in other mineral phases too. So I guess it does pay to sort of have a good detailed look at the laser ablation chemistry. And I guess in terms of where to next, our colleague, well, my boss Rick Valenta, he put together sort of a prospectivity map for primary exploration of rare earth elements. And certainly it's good to see that in this area that he highlighted as sort of one of the most prospective, that does correlate with our most prospective areas in terms of rare earth element abundance. And so we've got some ideas of where we'd like to go and continue our search. Now, I don't have time to talk about indium or indeed gold. The one thing I will say about gold, though, definitely does pay to look in your waste. I mean, we did furthest north I've ever been in Queensland. We went to the Horn Island in the Torres Strait, and this is material that was in their waste rock dump, and it had 33.7 ppm gold in this sample. So is that waste? I don't think so. So just pays to look in the waste sometimes for some of these materials. But it's also important to remember that for economic rehabilitation, you do have to define that there's an environmental problem. So this is showing a Ficklin plot of the samples that we took here. So I guess if you want to build that business case, certainly just don't forget that you do need to consider the environmental impacts the waste may have too in building that case. Now, a cool thing that happened this week in Queensland was the government announced a vanadium plant is going to power up to support the new economy mineral boom. And I guess all of this work that we're doing with the waste hopefully speaks to, seeing other plants like that perhaps being established in northwest Queensland for cobalt, maybe for rare earth elements. There's all these opportunities to sort of continue to build the minerals and the met sector in Queensland, but focusing not on coal, not necessarily on copper. Well, we're always going to focus on copper, true, but maybe moving away from coal, but maybe moving those mining activities into these cleaner energy technologies. But in terms of our mine waste investigations, we actually sucked for vanadium, so perhaps we've been looking in the wrong space, so that's probably somewhere that we need to go and start looking next. So I guess just to finish, I mean, there's, and you guys at Imperial are well across this, but, there's so many new technologies to actually enable that metallurgical recovery. And we're only just starting to get into that phase of our project now. So it'd be great to sort of, have comments or after this presentation, have people reach out and sort of just talk about their experiences with similar materials and how we can actually start getting the value out of these materials that we've now been characterising. So I guess the next steps we have in our project are to sort of really champion the sites that look like they could be sites that are going to see economic rehabilitation actually really kick in, and develop partnerships with METS companies to actually help realise that value. So it's not just falling into the chasm of death, it's actually becoming a real breathing industry, this kind of supplementing our need for critical metals using mine waste. So thank you for allowing me to talk today. Thanks for your attention, and there's my contact details. Just want to leave you with that concept that waste is a design flaw. So I'm going to try and stop sharing my screen now if I can. There we go. Thank you. Thanks very much.
Excellent. Thanks for that excellent talk, Anita. Oh, I can hear myself. Thanks for a really, really excellent talk covering a huge amount of content, and there's some applause there from the audience. We have to finish at 1 o'clock or 11 o'clock your time. So we've got time for there's a couple of questions in the chat, but if anybody has a burning question they'd like to ask, please raise your hand. Otherwise, I'll ask the questions from the chat. So from the chat, Tom asked, copper being a particular issue for tailings production, is that per unit mined or because it's a dominant resource? So why is copper such an issue for tailings production?
I think
it's quite early on in the talk, so I think it's when you were talking about the tailings copper.
I think it's just because of the grades of copper that are being mined and the sheer tonnage of copper that's being mined. I think that's probably why we see that major contribution from the copper sector.
I actually did this calculation for a school's talk yesterday. Because it was in 2019, there were 3 billion tons of iron ore or iron produced, and 20 million tons of copper. But if you go on 0.5% head grade, then that gives you 4 billion tons of copper ore mined. So then it starts to look equivalent to iron ore. It was one of those numbers that I thought would be useful to have. So there you go. And the Adelia asks, what sorts of processes could be in place to recover waste copper, which is a really good question, or any waste material, and how much energy on average can be used for this recovery, or would be used for this recovery? And could you use renewable energy to recover this waste?
I would love to. And I guess that was kind of the thing very early on, sort of thinking about systems thinking. So, if we're going to be, it's particularly in the land of Australia, like solar energy is quite, like I've seen some sites where, they start to introduce solar farms into some of those kind of open pits, and that can help generate sort of energy. And certainly the Kidston mine, they've got a they generate energy there too. So potentially you could generate the energy in one place to help sort of the plant run to recover the value in the other part. So that's possible. And I think another place where they want to do that is when they think about restarting Mount Lyell, they want to actually be a fully clean energy sort of place. I mean, they've got hydro, they've got the access to wind farms. So, I guess, yes, it'd be great if we could do that. And I don't think it's a pipe dream anymore. But in terms of, I guess, better technologies, cleaner technologies, people talk about bioleaching. I don't necessarily know if that's efficient, but certainly it's something that's talked about. Phytomining or phyto extraction is something that we've been looking at here. I guess they're probably two of the main things that we've been looking at so far, but I know that we've got a lot to learn from you guys in Europe because you are traps ahead down that pathway. So I'm keen for more conversations in that space. I'm using this almost as a pitch for give me your ideas, please. Yeah.
I know I have 1,000 questions about processing for you, but I think unless anybody's got any other questions, we will end the seminar there. Thanks everybody for attending. Anita, thank you so much for your talk. It's really, really enjoyable and insightful. Enjoy the rest of your day and evening. Thank you, everyone.
See you later. Thanks for having me. Cheers.